Suppose a random vector x has three components x1, x2, x3 with joint probability density function. F bold x of bold x equals e to the minus x3 on the region where 0 is at most x1, at most x2, at most x3. 0 everywhere else. This ordering constraint is the key feature of this problem. It defines a wedge-shaped region in 3 dimensions, not the full positive orthant. The 3 components are not interchangeable. Our task: find the 3 marginal densities f of x1, f of x2, and f of x3 by integrating out the other 2 variables in each case. Then decide whether the components are statistically independent. Start with the marginal of x3. Hold x3 fixed and integrate out x1 and x2 over all values consistent with the ordering constraint. Given x3 fixed, x2 ranges from 0 to x3, and for each x2, x1 runs from 0 to x2. The marginal integral is x1 from 0 to x2 inner, then x2 from 0 to x3 outer. Inner integral first. The integrand e to the minus x3 does not depend on x1. Integrating dx1 from 0 to x2 simply gives x2 times e to the minus x3. Now the outer integral. Factor out e to the minus x3 and integrate x2 from 0 to x3. That integral is x3 squared over 2. Multiplying together gives x3 squared over 2 times e to the minus x3. Result: f of x3 equals 1/2 x3 squared e to the minus x3 for x3 at least 0. Recognize this as a gamma distribution with shape 3 and rate 1. Next, the marginal of x2. Hold x2 fixed. Now x1 ranges from 0 to x2, and x3 ranges from x2 to infinity. Because x1 and x3 are on opposite sides of x2 in the ordering, their integrals are completely independent of each other. The marginal factors into 2 separate integrals. The first factor: integrate dx1 from 0 to x2. This simply gives x2. The second factor: integrate e to the minus x3 from x2 to infinity. Evaluating the antiderivative gives e to the minus x2. Multiply the 2 factors. F of x2 equals x2 e to the minus x2 for x2 at least 0. This is a gamma distribution with shape 2 and rate 1. Finally, the marginal of x1. Hold x1 fixed. x2 ranges from x1 to infinity, and for each x2, x3 ranges from x2 to infinity. Set up the iterated integral. Integrate x3 from x2 to infinity first, then integrate x2 from x1 to infinity. Inner integral. Integrate e to the minus x3 from x2 to infinity. The result is simply e to the minus x2. Outer integral. Now integrate e to the minus x2 from x1 to infinity. Evaluating the antiderivative gives e to the minus x1. Result: f of x1 equals e to the minus x1 for x1 at least 0. This is the exponential distribution with rate 1, equivalently, gamma with shape 1 and rate 1. Step back and look at the 3 results together. All 3 marginals are gamma distributions with rate 1, but with shape parameter equal to the index of the component. x1, e to the minus x, gamma 1, 1, the exponential distribution. x2x times e to the minus x, gamma 2, 1. x3x squared over 2, e to the minus x, gamma 3, 1. The shape grows by exactly 1 at each step. This is precisely the distribution of the 3-order statistics from an exponential population. If you draw 3 independent exponential random variables and sort them smallest to largest, the kth order statistic has exactly the gamma k, 1 marginal density, matching our 3 results. Here are all 3 density curves together on the same axis. Are the 3 components independent? The answer is no, and we can see this 2 different ways. Multiply the 3 marginal densities. E to the minus x1 times x2 e to the minus x2 times x3 squared over 2 times e to the minus x3. This simplifies to x2 times x3 squared over 2 times e to the minus x1 plus x2 plus x3, valid on the full positive orthant. Compare with the joint density. E to the minus x3 on the wedge 0, at most x1, at most x2, at most x3. The two expressions are completely different forms, and different supports. Therefore, x1, x2, x3 are not independent.